Today we are going to talk about material nonlinearity, and we'll start with plasticity. In the first lecture, we've introduced the material nonlinearity as a behavior deviating from linear elasticity. On the left, we have a typical yielding type of behavior, where under loading, the tangent stiffness becomes smaller, and then under reloading, we retrieve back the original stiffness, Young's modulus here in the one-dimensional case. For damage, however, we have a different type of behavior, and eventually in both cases we'll reach fracture. For damage and fracture, we will talk about them in the next lecture. In plasticity, the characteristic is that we can decompose the strain into two parts. One is a plastic strain, and the other is an elastic strain. So you can see their proportions under unloading. So the plasticity typically occurs beyond a certain level of loading, a stress level. For instance, in one-dimensional case, we have the yielding strength of the material, sigma 0. So once we go beyond this sigma 0, yielding starts to occur, which means that plastic strain starts to accumulate. Plasticity is a permanent deformation, irreversible one. So in unloading, this strain remains there. So this is very different from elastic strain, which is reversible. And as mentioned, we have this so-called additive strain decomposition. The total strain is considered the sum of the plastic strain and the elastic strain. The relationship between stress and strain is in rate form. This is the so-called flow theory of plasticity. Basically, it means that the incremental strain is composed of incremental plastic strain plus the incremental elastic strain. And then they are related through a constitutive law to the incremental stress. There are different kinds of plasticity depending on the influence of the loading rate. So if we pull the bar in a very fast manner, then we may have a different constitutive law compared to a slower loading. So this is the so-called rate dependency. We could have a plasticity behavior which is rate dependent, and for this lecture we focus on the simpler one, which is rate independent. As I mentioned, the onset of plastic flow is determined by a yield condition or yield criteria. In the one-dimensional case, it's very simple. You can write it just by this simple equation of sigma minus sigma 0. Once sigma reaches sigma 0, then yielding occurs. The plasticity theory includes both yielding and also a flow rule, which basically tells the direction and the magnitude of plastic deformation, or plastic strain, or plastic flow in the rate form. And then we could have hardening, which means that the yield criteria evolves with respect to the accumulation of plastic strain. So if the yield criteria does not change with respect to plastic flow, then we have a straight line here, which is the perfect plastic case. And in reality, however, most of the case we would have this type of curve, which means that our yield condition is changing with respect to the increase of epsilon p, and this is called hardening. So this hardening parameter, in this case epsilon p, is itself evolving with time. We need numerical algorithm to accurately calculate the incremental strain and the decomposition of this incremental strain into elastic and plastic parts, and the incremental stress and the tangent stiffness. Then we can make sure that in every increment we achieve equilibrium.